So what I want to do now is do a little thought experiment. Let's pretend that I have a proton. So here's the proton. Everybody can see the proton, right? It's in between my thumb and forefinger. Okay. Proton's here. I let go of the proton, and I see the proton start to accelerate. And the proton accelerates downward, and the acceleration is 9.8 meters per second squared. What's the proton interacting with? The Earth, right? And the Earth is exerting what type of force? A gravitational force. Okay, so the proton is falling with the usual acceleration near the surface of the Earth due to the gravitational force. Okay. Second case, I have the proton again, and I let it go, and now I see the proton accelerate to the right with an acceleration of 1 times 10 to the 11th meters per second squared. Do you think this is still a gravitational interaction? Probably not. If it were, what would be happening to the rest of us? We'd be all accelerating at that rate to the right? Because we all have mass, and if the proton has mass and is affected by a gravitational force, so are the rest of us. So there might be a supermassive black hole next to us over there, and we all be flying toward it. But if just the proton is moving, right, it's just things that have a net charge that are being affected. Neutral matter isn't being affected, so it must be an electric interaction. What could be causing that electric interaction? Okay, well, I heard a negative charge. Where would the negative charge have to be? On the right. Okay, so I could have a negative charge over here that's exerting an attractive force on the proton and causing it to accelerate to the right. Is that the only possibility? Oh, it could be a positive on the other side, right? We could have a positive charge over here causing the proton to accelerate to the right. Or could be both. Could be a combination of a number of different charges, right? Positives on one side, negatives on the other, causing the proton to accelerate to the right. Without looking around, we don't know. But we could make some other guesses. We could say that, let's say I remove the proton. And I'm going to just reference where it was by putting a little X there, calling it location A. Let's say I put a different particle there. Let's say I put an antiproton, which has the same mass but opposite sign of charge. What would happen to the antiproton? It would go to the left at the same acceleration, right? So because the same force is being acted on it. So we know that would accelerate at 1 times 10 to the 11th meters per second squared. Okay, so there's something about that location in space. If I take all the particles away and think about just that location where I put the proton or where I put the antiproton, there's some property or something about that particular location that causes a proton to accelerate one way, or any positive charge to accelerate to the right, or any negative charge to accelerate to the left. And that property is what we're going to call the electric field. So the way to think about the electric field is that it's a sort of a virtual force. You don't have to have a particle there to have an electric field. But if you do place a particle there, it's kind of like the electric field is sort of lying in wait, just waiting for a particle to come along and be placed right at that location. If the particle is placed there, if it's a plus charge, the electric field would accelerate it to the right. If you place the negative charge there, the electric field will accelerate it to the left. So we want to define this electric field, or this sort of virtual force, in such a way that we get the correct behavior depending on what charge we place there. So here's the definition. I'm going to write it this way. We're going to say the electric field we're going to indicate with the capital letter E. E, it is a vector. Okay, so it's a vector quantity. I'm going to write it this way. E sub 1 is equal to F sub 2 over Q sub 2. Now, what do I mean by these subscripts? Well, the way to interpret this is that this is the force on some particle, and we'll just call it particle 2. Q, what is Q? Q we use to indicate charge. Okay, so the symbol for electric charge we often use little q or capital Q sometimes. So Q is the charge, and this is the charge of particle 2. And so the electric field, we say, is the electric field caused by some other particle, caused by, well, I'll just label it particle 1, which could be somewhere else. It could be the negative charge that was on this side, or the positive charge that was on this side, or it even could be a combination of the two. Okay, but it's caused by something else, and this is a vector. Okay. So we're looking at a location in space. So let's write out some properties here. The electric field first of all, it's a vector. It has a magnitude and a direction. It is a property of a location in space. Okay, so we're always talking about the electric field at a location A, for example. It exists even if no charge is placed at that location. And it's created by other charged particles not at that location. Okay, and we'll talk about how other charged particles create electric fields in just a minute. Let's think about the directions of this thing for just a second. We said in our little thought experiment that we placed a proton at location A, and we saw it accelerate that way, which means the force, the electric force on the proton, has got to be in what direction? That way, right? It's got to be that way, just from what we know about Newton's second law, right? If there's a net force in that direction, it causes an acceleration in the same direction. What can I infer about the electric field direction at that location? Think about what this formula says. We're taking the force and dividing it by a charge. What's the sign of the charge at that location A? Positive. Okay. If I divide a vector force by a positive number doing scalar division, I'm going to get a new vector that points in the same direction. Okay. So that means the electric field at this location, say E at location A, is pointing to the right. Okay? The key idea is that stays the same even if I take that particle away. So now I remove the proton. I still have this electric field pointing to the right. I place an antiproton there. So now this charge is less than 0. And now I could figure out what the direction of the force is, because I could write that the F2 is equal to Q2 times E1. So in other words, this is relating the electric force to the electric field. E1 is pointing to the right. Q2 is now what sign? It's negative. So if I multiply a negative by a vector, I get a new vector that points in the opposite direction. It's going to be pointing that way. And so we get a force, just as we said before, we're going to get a force on the antiproton in the opposite direction, causing an acceleration in the opposite direction. But the electric field stayed the same. Okay, that's the key idea. So a proton is placed at location A, and it experiences an electric force in the direction shown. What's the direction of the electric field at location A? And pretty overwhelming vote for direction 8, which is correct. You place a proton there, okay, and the force is in direction 8. And so just from our definition of electric field, just reasoning from the formula without even having to plug any numbers here, we know the direction of the force. We're dividing by a positive or a negative. Dividing by a positive, so the new vector, the electric field, should be in the same direction as the force vector. Okay, so direction 8 is correct. Okay, questions? Let's try a numerical example. There is an electric field at a location A due to some charged particles nearby. And you place a proton at A, and it experiences an electric force of 0, negative 4.8 times 10 to the minus 16, 0 newtons. What's the electric field at location A? So the proton's charge is, again, positive E, little e, 1.6 times 10 to the minus 19 coulombs. Okay, pretty clear. It's got to be 0, negative 3 times 10 to the third, 0 newtons per coulomb. We're just simply plugging in and chugging, right? Notice the units here, units of electric field are, there's no special name for these units. It's just force divided by charge. So newtons per coulomb are the units of electric field. So we have, what do we say, 0, negative 4.8 times 10 to the minus 16, 0 newtons divided by 1.6 times 10 to the minus 19 coulombs gives you an electric field of 0, negative 3 times 10 to the 3, 0 newtons per coulomb. And we divide by a positive charge, we get an electric field that points in same or opposite. Negative, negative, so that's the same direction, right? Dividing by a positive charge, we get a force and an electric field that point in the same direction. What about this case? At location C, we have an electric field shown in the direction indicated due to charges not shown. We place a chloride ion there. A chloride ion has a single negative charge, singly charged. So what's the direction of the electric force on the chloride ion? And it's got to be in direction 2, right? If we place a negative charge there, and we know the direction of the electric field, we're trying to find the direction of the force. Negative charge times a vector gives us a new vector that points in the opposite direction of the electric field. Okay? This is okay, right? No problems here? Okay.